I want to do instead is move on to the topic at hand, which is trying to get to a discussion about amino acids and proteins. But in order to do that in the context of all of biochemistry, first I have to fit proteins and amino acids into a broader context of biological polymers responsible for life. And I would argue that there are really 4 classes of biological polymers that form the basis of life on Earth. You've probably seen this in some capacity in your high school biology course, and maybe you saw it in 701. But the first group, as you are all well aware, right, of course, are lipids. And these are simply alkanes or alkenes that also have a carboxylic acid group. Okay. So, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. This is an example of palmitate. Palmitic acid. I'm calling it palmitate because I'm drawing it in the anionic uncharged form, C16H32O2. Okay? That's one class. Now, sometimes these are esterified to a polyalcohol, to glycerol, and when that happens, we call them triglycerides because it's the glyceride part is the glycerol polyalcohol. But that's one class of molecules, okay? Alkanes and alkenes. Second class of molecule are carbohydrates. And carbohydrates are literally hydrates of carbon. They have the general formula CH2ON. Okay? And for the most part, these are polyalcohols that either have a ketone or an aldehyde on them. Okay? And an example of that, for instance, that you are all familiar with is that terrible evil molecule glucose. 4, 5, 6. Now, you will notice how many of these carbons that I'm drawing here are chiral. Color this a certain color. Okay, so this, of course, is simply D-glucose. Is it an aldehyde or a ketone? I can't hear you. It's an aldehyde, right? And you remember, I hope, that aldehydes can react, get a different colored piece of chalk, with alcohols. And when I have an aldehyde and an alcohol, aldehyde plus an alcohol, I end up with what? Okay, and this is called a what? Hemiacetal. Right? This is a hemiacetal. And so, although I've drawn glucose for you this way, you can easily imagine what happens which is that this hydroxyl can react with this carbon, and in doing so, give rise to this structure. That's got it. This is called alpha D-glucopyranose. It's one of two forms, depending on where I choose on the stereochemistry at this center here. But this is an example of a cyclic hemiacetal. And as you'll learn, I can make long polymers of these. And again, long polymers of these polyalcohols that are essentially cyclic hemiacetals or cyclic hemiketals. That's the second class of biological molecules from which life is based. The third class of molecules are polynucleotides, which of course, nucleic acids, as you know, which are really nothing other than polyesters. So we've seen alkanes, we've seen polyalcohols, and now I'm telling you that the next group is polyesters. Question? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You're correct. O minus. Thank you for catching that. Okay. Polyesters, okay, as I said, which consist of polymers of the hemiacetal form of a 5-carbon sugar ribose linked by phosphates. And in this case, what we're talking about is a structure that looks like this. The base. And the 5-carbon sugar ribose has a C1 prime substitution. We will go through this in detail later in the semester. C1 prime substitution with a nitrogenous base. It continues down up here, and it continues down here. Okay? And of course, you can see here's one ester, here's a second ester, and so these are phosphodiesters. Okay? So these are polyesters. And the last group of molecules on which life is based are proteins. And proteins, of course, are nothing more than polyamides. Polyamides of alpha amino acids. Okay? Everybody still with me? So all of life comes from 4 types of polymers. Alkanes that have carboxylic acids, polyalcohols, polyesters, phosphate esters, and polyamides. That's all we need in order to create life.